We're delighted to have Aram Harrow, who will moderate the panel, what quantum can offer to AI. And Aram is a professor of physics at MIT. He's the founder of the HHL algorithms for solving linear systems and quantum computing. He works on a project, or is a PI for our project for quantum and AI, alongside of Kristan, Temme, who is a research staff member, and Peter Shor, who is the Moore's Applied Mathematics professor at MIT. So welcome. Thank you very much.
Great. Thanks, Lisa, for the introduction and for putting this together. We're all excited about this panel. The idea is to have 3 quantum people and 1 machine learner.
It's not fair.
It's stacked from the beginning. Have a conversation about how these fields could work together. One of the last questions you got, which was not from us, was substantial computing power is needed, and we hope that quantum computing can be part of that answer.
I hope too.
Hopefully, so hopefully we'll get to some ideas for how that might work. And the way I thought we would do this, so I'm going to moderate and introduce the whole thing, and then maybe we'll have a little conversation between the 4 of us. And I want to leave a lot of time to open up to questions, because I think that many of you probably will have questions about how quantum computers work and what we can hope to get from them. So let me just begin by saying very briefly, if you don't know, if you haven't heard of quantum computers, or if you've probably heard of them. Yeah, here's so I put up a few equations that might be useful. They're pretty self-explanatory, but the idea, the way I like to put it, is I would not explain the power of quantum computing in terms of entanglement, although I think it's a necessary part. But I would say it changes. Quantum mechanics can be thought of as a generalization of probability theory. So if you have a classical computer with n bits, that's got 2 to the n configurations, and we know already it's useful to randomize things on classical computers. We've both empirically and theoretically, there's a lot of evidence that randomness helps. And you could think of it as you've expanded the state space. Instead of just having 2 to the n possibilities, a probability distribution is a vector of length 2 to the n of real numbers that are non-negative and add up to 1. And what a quantum computer does, and sorry, this lets you explore very large state spaces. So if you want to do high dimensional integration, you're adding up an exponential number of points. It would be foolish just to add them up one by one. You're better off sampling, which really means relying on a probability distribution to explore this exponentially large space. We kind of take that for granted, that this has sort of been, we've learned it so well that we forget that there was that this is actually an advantage to use randomness. What quantum does, it says, if you have n qubits, instead of 2 to the n probabilities, you have 2 to the n amplitudes. And these are like probabilities, and they're normalized, but they're normalized in the 2 norm. So they're complex numbers, and the sum of their absolute values squared adds up to 1. In fact, their complex doesn't really matter. If it was just positive and negative real, you'd already get the idea. And the reason why that's special is that if you have a probabilistic machine, then you can take different paths through the machine. And if there are many ways of getting to a particular outcome, you just add up all the probabilities that reach that outcome. On a quantum computer, it's the same thing. You add up the amplitudes that reach an outcome. But now, if let's say some of these amplitudes are positive and some are negative, they can cancel out. And so you have an interference phenomenon like you do with waves. With these lights, I can only see the first 2 rows. So I hope you're getting this. They interfere like waves. So when waves interfere, they can interfere constructively or destructively. If they're in phase, let's say they're both positive or both negative, that's constructive. If they're out of phase, the opposite sign, they cancel out. And that's just a richer set of phenomena than you get just by things that add. Right? So light interferes, paint just adds, the colors just add. And so that's sort of the difference between quantum and classical computing, is this richer set of possibilities. And in some cases, we know how to do really exciting things with this. Peter Shor found an exponential speed up for factoring, for example, that could have a lot of important implications for cryptography. There's also less than exponential, but still big speed ups for things like unstructured search. So if I have a function that has n possible inputs, and I want to find which input gives me the maximum, and I have no I can't use gradient descent. Let's say that there's no useful structure to exploit. Then it sounds like I just need to evaluate it n times. On a quantum computer, I can evaluate it square root of n times. So those are the types of things where we know provably there's a speed up on a quantum computer. And now the question is, how do you use this power for machine learning? And we have a research project together that's investigating this. The title of this session had a question mark in it, which reflects the fact that we don't really know the answer. And I'm going to stop abusing my role as introducer, and I'll pass the torch to the others. The last thing to say is, I have a perspective on how I think machine learning people should think about the power of quantum computers. Because the quantum computers that we're going to have soon are going to be pretty small. And even in the long run, a qubit is probably going to be more expensive than a bit. So we're going to have trillions of bits just on your laptop, and maybe millions of qubits. That'd be an ambitious thing to have. And so what can you do with something that is much smaller than your existing computer, but has much greater capabilities? Now, one challenge is that we don't exactly know all the algorithms that we get speedups for on a quantum computer. I gave you a few examples. There are more. In some cases, we know you can't get a speedup. In some cases, we know you can. But I think it's possible to leave that to the side for the moment. So suppose you have a 1,000-qubit device. And you know it can only run 100,000 operations. So for a classical computer, that would be very pathetic if you had that. But these 100,000 operations are extremely powerful, right? Each one can process the data in ways that would not be that go far beyond what a classical computer could do, maybe even exponentially faster. But it's still not very much data. Already that tells you something useful. That sounds like you might want to apply it to a problem like cryptography, where you have a small little secret key, and you want to extract, you want to break the code. Or maybe something like quantum simulation, which we know has exponential difficulty. Classical computers have exponential difficulty to do. It doesn't seem like something you might apply to classifying 1 billion images, because the quantum computer just can't store that much data. And it doesn't even have time to have it stream through the quantum computer. So I think already this tells you something, as if you're a machine learning researcher and you want to say, what problem might I use a quantum computer for? Already it steers you in the direction of what is a problem that doesn't involve very much data, but is very hard. So it has a small input size, and yet there's some extremely difficult computation to do. Just because, and then that, I think, is the opening of a conversation. So once you have such a problem, then quantum computing researchers can say, well, here's what we know about how to solve it. Here's, we can try and come up with new ideas to improve it. But I think that is a good starting point. OK, so with that in mind, maybe we can ask Yoshua, what problems can you think of that would be important to machine learning? Not very much data, less data than a baby
So
gets.
I haven't thought about this a lot.
Yeah.
So it's going to be very naive, probably.
Yeah.
OK, so 2 things I've thought about while you were talking. One was planning.
Yeah.
Because you don't need a lot of data to start with, right? And you only need to have one answer that depends on the result of all those paths being somehow combined. So I don't know if this is an avenue that people have been thinking about. It's like the search problem, but you don't want to consider the paths independently like you would for searching a key, right? There's lots of paths that join back in the future, and you want the sort of a function of all the paths together, right? So it sounds like maybe it could fit. And the other thing I was thinking about is a bit more crazy. So I think of a quantum computer as a machine that does computation that would be very difficult to approximate with a classical computer, right? So there's an analog on which I've worked, which is a deep net does computation that a shallow net cannot imitate easily, right? So it happens in the case of the deep net that there are functions that can be represented by a deep net, which are really useful. And if you try to learn those functions with a shallow net, it just doesn't work very well.
Maybe even exponentially work.
Exponentially, in fact.
Right.
We have theorems about that.
Right.
So maybe something similar could be applied in the case of quantum computers. So for this to work, you would need to be able to train the quantum computer to learn functions which maybe classical computers can't do easily, but quantum computers can. I have no clue whether there's such a thing, but you might train them and see what happens.
Cool.
Now the question is, how do you train a quantum computer? I don't know.
So maybe, Kristan, do you want to? I think that second question sounds like our paper a little bit, doesn't it?
A bit, yes. So, okay. So we've been looking at certain networks, basically based out of circuits that we plan to train classically.
Okay.
Where we basically use the quantum computer to represent little data in a very large feature space, essentially. And I don't know whether this is what you were thinking along, but there are certain properties. Basically, what we were focusing on is essentially that would make these like querying or basically getting access to this large feature space very, very hard classically. So that doesn't necessarily mean that it's immediately relevant to a given set of data, but it basically paves the way of thinking along a particular line. Is there a very efficient way of accessing properties of the data in a quantum setting that you wouldn't have access to in a classical setting, basically? Or is there a way of basically representing data in a very high-dimensional space, coming in with little points and blowing that up in a very specific way, and which would be computationally too expensive for you to do classically?
So why do you want to do this mapping to this intermediate space story? Sounds like a kernel machine.
Right, exactly. But say, for instance, suppose someone gave you a particular kernel that is able to estimate, or basically that's able to represent features of your data that you couldn't represent classically beforehand. Right? So you could imagine that
So a hard to evaluate kernel.
It's a hard to evaluate kernel. You can look at that and. Looking at that,
so you mean even the dot product is hard to
correct. This is exactly the point. So especially when you look at this, okay, there are many easy kernels you can look at.
Right,
you can
right.
look at RBMs. You can do other things. But imagine there might be kernels where you say, I'd like to have a feature space that characterizes something in your data that is very hard to get access to. And in principle, the only way you would know classically of how to do that is to write down your ginormous feature vector and compute the inner product by hand. And so this is one thing that a quantum computer could essentially do for you by estimating those inner products rather
how do you figure out what that feature space is?
Yeah, that is a difficult question indeed.
So what I'm proposing is you learn it.
Right.
So the way I think about it is not like thinking about some feature space, but more a computing machine, right? Takes inputs, produces outputs like usual neural nets, except that it has these particular computations going on, which would be very difficult to emulate on a regular computer.
Right.
And now the question is whether the type of computation that is going on there actually is something desirable for solving real-world problems. But you could test that experimentally, right? You could test that by training them.
Correct.
And maybe find some tasks for which they're doing a lot better than the equivalent, not equivalent, but some normal neural net, which is classical, and doesn't exactly replicate the other guys, but potentially could still do a good job on that distribution, on the data distribution.
Correct. So where in that picture, you'd say you take the circuit essentially, and or you would take the quantum computer, tweak it to match the data. Indeed,
exactly,
this is a very of course. This is very,
so I guess
very
one
good
question
point, yes.
that's related to this is, I hear about all these qubits, and it would be much easier to train these things if they were continuous.
Sure.
Are there some like continuous quantum machines?
So people have thought about continuous quantum machines, and this is related to, I guess, coherent states rather than qubits.
Yep.
But it's really, people have thought about it, but it seems really very difficult to make them actually work and...
You mean to build them, or?
No, I mean, you could probably build them, but to make them actually do useful things.
Well, but if you train them, that's how they get to do useful things.
Right, yeah. But, I mean, this is also why we don't have continuous classical bits rather than, we use discrete classical bits rather than continuous classical things. We could build continuous classical things, but, it's much easier to design a gate that just takes 2, 0 and 1, and 0 and 1 and does something, than design a gate that takes a whole continuum of things and another whole continuum of things and produces some continuous things that's useful.
So the reason I'm proposing this idea is because I've been working on something, not quantum, but now analog for analog circuits. Right? So one problem with analog circuits is that they don't do what you want. In the sense that the actual devices have very complicated physics that don't correspond to neat things like multiply and add and take exponentials. But they do something which is a nonlinear computation. And if we could only tweak their degrees of freedom end to end to do the right thing, you could train them. So in my group, we designed a procedure for doing this, which doesn't require analytical knowledge of the actual physics that's going on under the hood, only that you can measure things locally, like what we call sufficient statistics, and inputs and outputs, and whatever is going on, we're going to tweak it so that it does better fitting the data.
Yeah.
And so maybe something like this could be done for quantum circuits, but they would have to be continuous.
So there's an interesting reason in terms of continuous variables in quantum computing. There's a particular reason, as Peter said, why like practically also why people like discrete structures in quantum
Also
computing.
for regular circuits.
And that is, quantum systems are very noisy inherently.
Yes.
And if
also
they're
regular
discrete,
circuits.
also right.
Yeah.
Yes, and you really notice in quantum systems, right?
No, I don't know.
And the way you fix this is by a procedure called quantum error correction.
Yes.
And they
So
quantum error
I
correction.
wouldn't try to fix it. That's the thing, right? You guys in the discrete world are always trying to fix the problem
Right.
by these some error correcting schemes. Whereas if you think in a machine learning way, you think, no, I'm not going to fix to have each piece do this idealized computation. I just want the overall circuit to do the right thing. And how can I tweak the different parts just a little bit so that it does?
Actually, there is something that,
No, go ahead.
Go ahead.
Sorry.
well, there's something that people have been looking at. So there's been a big focus as quantum computers start to be built. We might have an algorithm paper that takes 1 million qubits, but we want to say, what can you do with the 50 that we have here today, or the 20 or 100 or whatever? And one thing that a lot of people are looking at are called variational quantum algorithms.
Okay, what is that?
So what this means is basically you have a bunch of knobs that you turn to design your quantum algorithm. So the algorithm,
Sounds good.
Yeah. So the algorithm might be shine a laser at this ion for time t1, then shine a laser at that ion for time t2, and then adjust the frequency to an angle, omega 1. And all these things, t1, t2, omega 1, are parameters.
Yes.
And so you run your quantum circuit, you see how well it does on your objective function, and then you take a derivative. Maybe you do, or you have an outer loop. You do gradient descent, or stochastic gradient descent, or I'll probably stop talking about the options here.
It's not a trivial part of the question to get these gradients, but go on.
Not at all. No. And the advantage of that is it may achieve some of what you want, which is if the quantum computer is imperfect,
Yes.
and you're just doing your gradients based on the observed behavior, then to some extent what you're doing is you're training for that particular machine and for all of its imperfections.
Right.
So there may some of that we may have stumbled into something like that in our goals to find something for near-term computers.
Yeah, so near-term computers are going to be very noisy, or at least quite noisy. And if you want to do all the machinery of error correction, instead of having 50 qubits, maybe for 50 real qubits, you need 1,000. 50 logical qubits, you need 1,000 real qubits.
Oh.
So for near-term quantum machines, we're not going to be able to do error correction. So what we need is these techniques like you're describing that we can use the noise to get results rather than trying to fight the noise.
That sounds interesting.
Yeah. So actually, I'll say one thing about your first proposal of planning as well.
Right.
So there is a known, I mentioned that there's a square root speedup for unstructured search. This is one of the first algorithms that got people excited about, along with Peter's factoring algorithm, got people excited about the power of quantum computing. And since then, people have found quadratic speedups for many, many problems with little to no structure. And one of them, so you could think of unstructured search as taking the OR of n variables. right? Is there a target in any one of these n locations? You could also do an and/or tree. So you could say, take n variables, or them to get down to n over 2, then and those to get down to n over 4. And what that looks like is it looks like a two-player game. I make a move, then you make a move, and so on. And then at the end, there's some function that tells us who won the game. And it turns out quantum computers can also get a square root of n speed up for that. And that comes a little closer to your planning. This might be planning in an adversarial environment. But if you replace the adversary with some model of nature,
that's right,
there could well be a provable square root speed up. And then we might hope that heuristics would do even better.
So I want to make here the connection with something I mentioned in my talk earlier, which is that I guess there's not going to be ever enough qubits to represent the full richness of the state of the world, right? That you would be planning in. But I think we don't want to do that anyways.
Right.
We want to build AI systems that are planning in just the right dimensions and aspects of the world that are relevant to the plan, because I need to plan about how to get back home in spite of the fact that my flight has been canceled, actually.
Right.
Does that happen?
It's a true story.
So maybe it's actually a blessing that we have less
to,
data for quantum computers.
Well, maybe. But I think we need to rethink how planning is done. That I believe will be needed anyways for AI.
So I noticed our time just decreased a little bit. This is, it's OK. This is the amount of time including questions?
I think it's without
questions.
Okay.
So after this, we have another 10 minutes for questions. I kind of wanted a lot of time for questions.
So you can start. Yeah.
Can we just start doing some questions, and then we can come back? So hopefully you guys have been texting them in. You want me to answer this question? Yeah. I see. Like this plus 20 minutes for questions.
OK, good.
Oh, then maybe should we keep going until?
Yeah, we should keep going.
OK, we'll use up. All right. So questions will begin in 4 minutes and 43 seconds. So prepare yourself. So for the planning, so I guess the question is.
How does this work? Like I know so little about quantum things. Like how would you do something like what we discussed, that you basically considering an exponentially large set of paths through some state space.
Right.
Those paths intersect in the sense that they come back to states that other paths visit.
Yeah.
And there's some quantities that are going to be computed at each of the nodes on this graph, right?
So. Right, and even on a classical computer, there's a combinatorial explosion of paths.
Right. So in a classical computer, the problem is that the number of nodes is exponential, and we don't want to consider all of them.
I should say with this I opened with this idea of wishful thinking.
Yes.
So the wishful thinking is that the quantum computer can explore the exponentially many things in polynomial time. So we know that generically this isn't true. That classical computers we think can only do this when there's some structure. Right, if we think that p is not equal to np, we think you can't do it in the worst case. But we have these heuristics that tend to work pretty often a lot of the time. And so I think something was similarly true in quantum computing, that it will not always work, but this gives us an idea of where to look for some structure that we can get a handle on.
So current methods used in machine learning involve sampling to deal with this. And then a lot of the intelligence goes into sampling just the right paths.
Important sampling and
more intelligent than important sampling.
Right, but in that direction.
Yes. Right. Basically, you're learning a policy that figures out which direction should be explored. But,
Right, and I guess the question is, what I wonder is if there are models, so there are families of models that are not being looked for because they're too computationally expensive. So it seems like there's a lot of things in machine learning where you train a fairly simple class of models, and it does well because you have a large amount of data to feed in. But I wonder if for quantum we might look for a richer class of models, maybe harder to train on a classical computer, ones that we've even maybe given up on training on classical computers, but where in return we can't train it on as much data.
Right. So the only way I could see that this would work is that the quantum computer is not used for doing the whole training. It's only used for one particular computation, which maybe happens on a per example or per mini batch.
Right.
So that's the advantage of planning. Like you actually need to plan at each time step.
Right.
And that itself is an expensive computation. If we need the quantum computer to look at the whole data set, then it's hopeless.
Right.
So let's not do it.
Right. But already it seems classical algorithms have thought a lot about that, about, how do you sample many batches that are
Right. Mostly randomly.
Right, right. But maybe as you learn, that tells you with which weights to do the random sampling and so on.
So maybe the thing that's closest to what you're talking about is active learning methods, where you, or even exploratory policies, where you decide where in the state space you're going to go and get examples.
Right. It seems that I guess we have to think about. It seems like one thing that we may want to think about is how a big classical computer can work with a small quantum computer. So if the big classical computer is the custodian of a large amount of data, maybe it can interpret the outputs of a quantum computer as saying, oh, this is the type of data which I need to next feed into the quantum computer to train it.
Well, I mean, the other option is to combine the classical part and the quantum part. So let's go back to the hypothesis, and I have no clue if it's true, that there are some computations that are useful and can be only done by a quantum computer efficiently. So maybe we could extend this hypothesis to there are some computations, some functions which have part of it, which is small, needs to be done by a quantum computer, and the rest could be done by classical.
Right.
And then if we did this thing where we could train end-to-end the quantum computer, we could also train end-to-end with some other pieces that are classical, and then it might work even though you only have a very small quantum computer.
Yeah, that would be good to look at.
Yeah.
All right.
All right.
We have questions.
Oh, that's good.
Yeah.
What can AI do for quantum?
Who wants to take that one on?
So okay, I can. So there's various places where in the actual experiment, for instance, there are certain tasks where you have to discriminate when you measurement data, where you have to tune up gates in a particular way. And there are certain tasks that need to be automated. That is, for instance, a very good place for classical AI algorithm to help out what the quantum computing machine actually does. So for instance, you could use literally binary classifiers based on that use the measurement data that you get from a quantum circuit to predict whether the qubit state was in 0 or 1 when you measured it. You can come up with circuit optimizers that basically take in data from previous runs, from previous tune-ups, and basically go and only gradually tweak up the circuit in the next run, and the device in the next run. So there's a lot of use of classical AI techniques when you want to basically control a quantum experiment, and when you want to read out data from quantum experiments. So that's actually being done right now. So that's very useful.
So is it mostly predicting a few real values, or are you into predicting more complicated distributions?
So it varies. So there's multiple. I mean, there's multiple. So in the simplest case, it's just it's just plus or minus 1. Is it qubit 0? Is qubit 1? When it gets more intricate, it's basically that you have, and in these quantum devices, you have slightly noisy measurements. So although your quantum state was in a given state, and you measured the state collapsed, and you produce some outcomes for this, there's crosstalk and noise among different qubits, and it's really helpful in that setting to use classical AI techniques to basically filter the classical errors and the classical noise that you have by reading out the qubits in the end after the quantum computation has happened, to use machine learning techniques for that.
So can you also use machine learning for error correction?
For decoder, so people have thought about using machine learning for coming up with decoders for error correction, indeed. So that you think, so if you go back to the quantum coding setting, that there are certain tasks. It works in a particular way where you measure certain syndromes, And then basically, there's ways of using machine learning techniques to learn decoders in a way. That is also work that has.
And how do you get the ground truth for?
So the way you do this, the way you would do this in that setting is basically you prepare particular logical states and you know what you want to get out in some case, and then train your decoder in that setting. Yes, indeed.
I should mention that the word quantum in some contexts is just used to mean quantum computing. But in my department, everyone is doing quantum something or other. And so there was recently a meeting in the physics department where everyone who had some use or interest in machine learning came together. And people were using it to analyze LHC data, to predict material properties, to model nuclear physics. It's kind of amazing how almost every branch of physics, and physics is mostly quantum physics, is using AI in some way. So I think even beyond quantum computing, there's a lot of interest in using AI for quantum physics applications. So I guess we don't have to always do the top question. They're pretty close. They're pretty close. And so anyone can at any time grab any of these questions. Should we talk about rethinking the computing stack?
Okay.
Peter, you want to talk about that?
Yeah. So, so a quantum computer. So the classical computer stack is very well worked on. Quantum computer, we have, we're part of an SF grant that is going to, think about how do you build a quantum computing stack. And one of the things we've realized is that the different pieces of the stack are much more tightly connected than they would be in a classical computer. And somehow you have to, design the stack to take advantage of this.
Yeah.
And and
I guess one interesting part of it is even there's a lot of classical computing circuitry that goes into it.
Right.
Like Kristan mentioned error correction, because you have to measure, diagnose, and correct the error and feed that back in, as the computation is running.
Yeah.
And then maybe your quantum computer is at 1 or 2 Kelvin, and so you have classical circuitry. It has to communicate with the room temperature computer. There's a lot of challenges there.
By the way, as a parenthesis, machine learning-based software also doesn't really fit well in the standard computing software engineering framework because, for example, the pieces interact a lot with each other. They can do the wrong thing, and yet overall it looks like everything is fine.
Right.
The traditional ways of testing and independently debugging pieces doesn't really work well with machine learning. So there's also effort to rethink the computing stack for machine learning, which is not trivial.
Right. Yeah, and one of the more difficult things about the quantum computing stack is debugging because if you measure something, you've affected your computation. So you really need to make these very careful measurements that measure, certain things don't really affect the computation, which is, that's basically a piece of quantum error correction, and that's really difficult to figure out how to do in all cases.
Right. I guess it's already an issue with the quantum experiments. Like if you want to build a magnetic field detector that's extremely sensitive, often the best thing to diagnose it will be the detector itself. So that's definitely a new challenge in building quantum computers.
Okay.
Should we talk about different approaches?
Sure. So shall I? Yeah. So
Sure.
There are different approaches to quantum circuit development. So I guess IBM, Oxford, photonics, et cetera. And the question is, does the type have any real advantage for AI over a different type? Well, classical computers, it really doesn't matter what the bottom layer is. They can more or less do all the same thing. And the same thing is more or less true for quantum computers. The big difference, I think, between the architectures is how easy it is to go, to get a piece of information from one piece of the quantum computer to another. There are some architectures where, at least for small computers, everything is very well connected, whereas for some superconducting architectures, you need to send this piece of information to the next qubit, to the next qubit, to the next qubit, and all the way along the chain before you can get it from one side of the computer to the other. And these are going to have a big effect on which algorithms are best for this structure. I'm not sure which I'm not sure how that's going to interact with AI.
Right. It may also be that for a large quantum computer, some of these differences will wash out.
Right.
Because if you want to, the requirements of quantum error correction, we were talking about it before, how it's a little bit like a rocket ship. 95% of its mass is the fuel. A big quantum computer may spend 95% of its time correcting errors. And so in that sense, all the architectures will have to come to terms with that. And the connectivity, the resulting connectivity will look very different than the underlying physical one. So
there was a question, can quantum computing be applied to Monte Carlo approaches for Bayesian inference and optimization, which is related to my earlier question for planning. It's sort of a similar kind of question.
Go ahead.
Sure. So there's a way of, as Aram explained earlier, there's a method called amplitude amplification, right? So this specifically makes use of the fact that you have negative numbers and positive numbers. And that can be used in many classical Monte Carlo routines by providing, say, immediately a squared speed up in burn in and in mixing times. So there's a direct way, basically, if you have a classical Monte Carlo chain, a classical Markov chain that you want to run, and you want for various tasks, there's a way of immediately using a quantum computer just by to speed up the burn-in time, and B, to actually also get a quadratic improvement in terms of the sampling complexity.
So one question I have about this is, so let's say you want to do just a simple Monte Carlo integration. Is the integrand going to be the thing that the quantum computer computes? Because in general, it's going to be hard to put into your quantum computer, no?
Oh, it depends. So yes. So all these basically require really large computation. So
right.
So as Aram and Peter mentioned earlier, there's goals for near term. And this type of speed up, you would look for something that goes further out.
When we have really large quantum computers.
Correct. When you have a reasonably sized. So.
But then the answer to my question then is yes, that we would have a quantum computer that implements the integrand that we want to.
That you want to sample from, right? In terms of yes. So you have a circuit that essentially queries that function.
Yeah.
And then there's various techniques to boost the probability to basically see certain events.
Okay.
And so just to add to this, so you might say, if you want to sample from something, there's a naive thing, which is you could do rejection sampling, and then something a lot smarter would be like Metropolis, Markov chain Monte Carlo. And if you look at the quantum, when I said the quantum can speed up the OR function by a square root, a similar argument can speed up rejection sampling by a square root. But that's not so impressive if the leading classical algorithm looks like MCMC. And so with more effort, you can also quadratically speed up MCMC. And that's kind of a big goal in a lot of quantum algorithms research is, at least at a baseline, whatever the leading classical thing is, we hope to get a quantum square root speed up of that. There's one more thing you can do with this, which we, I think, understand a little bit less well, which is at the end of MCMC, you get a sample from your target distribution. And at the end of the quantum process, when it works, you get something called a Q sample. That's a lot of our nomenclature or names of our institutes. There's Qs all over the place. So what a Q sample is I said amplitudes, they're squared add up to 1. So what this is you take your target distribution and just square root all the probabilities, and you call those the amplitudes. And what good is that? So one thing, it can give you an ordinary sample. If you measure it, it just yields you a sample. So it at least gives you that. But there's some things you can do with it that are exponentially more powerful. For example, if I have samples from a distribution and I want to know, is this close to the uniform distribution? This is related to the birthday problem. I need square root of n samples. But if I have a Q sample, I can do it with one sample. I can get sort of constant bias answer to that question. And there are many other things like that. If I want to know if two Q samples are close or far apart, I just need one sample of each instead of a number that grows with the size of my sample space.
So in general, can you do the average over a large number of samples in more efficient way than doing them individually and then adding?
So let's say you can Q sample from many. If you can Q sample from many things, can you then Q sample from their average?
So in Monte Carlo, we normally just do a mean over many samples, right? This
right.
is the thing we care about, not necessarily just the individual
right.
samples.
You can estimate the means also with quadratically fewer samples.
Okay.
So there are, and I think this type of thing we have not people have laid the foundations for this, like showing you can do these sort of building blocks, but I don't think we've used them yet, and people have not yet quite figured out how to use these building blocks. So that would be, I think, really cool if we could connect those better to applications. We keep skipping this. Oh no, we answered the purple one. Should we answer the floating? I mean, the floating point, qubits can represent whatever you want. I mean, qubits can represent JPEG if you want.
But the question is, can you have like
just expensive.
Can you have a continuous version of a qubit?
Oh, so well, there are two ways of doing floating point. So one of them is if, let's say a floating point number on my classical computer is 64 bits.
Yeah.
I can allocate 64 qubits to that.
Yeah.
And then it could be in a superposition of different values. It's just probably not the best use of my qubits, but I certainly could do that. Then I guess we talked about this earlier, that there are these sort of quantum computers with continuous degrees of freedom. Error correcting them, as Peter said, is harder, not impossible. The Yale group with their superconducting qubits is really pushing hard in this direction. But what they're doing is sort of at the lowest level, they might be using continuous degrees of freedom with some error correction. They're using these to then encode logical qubits, which are then used in the calculation.
I see.
The issue is if you have, and here's the same for analog, if 0 and 1 are the only allowed values, if you find your computer says 0.98, you can push it back to 1. If any number between 0 and 1 is legal, and your computer is 0.57, how are you to know whether it should be 0.56 or 0.58?
Well, you might have a prior.
Right, but it's, there may be things you can do. And also maybe AI algorithms are inherently a little noise resilient. So
yes.
I'm not saying that there's a, maybe what I should say is, I'm not saying you can't use the floating point. I'm just saying we have not come up with good answers yet on how to use it.
That's interesting, yeah.
So shall I take this one?
Sure.
In July, an 18-year-old Yuan Tang proved that classical computers can solve the recommendation problem nearly as fast as quantum computers. Thoughts? Well, I mean, my thought is, we had a very clever algorithm for the quantum computer for solving the recommendation problem, but it turned out the recommendation problem wasn't anywhere near as hard as we thought, and the classical computers could do it. So I don't think this shows that, no, in general, classical computers can solve problems as quickly as quantum computers. I think it shows that we should be more careful about claiming certain problems are hard when we find an algorithm for them on quantum computers. Right. And this has happened before. We found, Ed Fari found this QAOA algorithm and showed it could do something that wasn't known how to do on classical computers. And then a bunch of, I think, half a dozen.
I think 10.
10 really smart computer scientists came up and found an algorithm for doing it on classical computers.
Yeah. Actually, what happened is he asked them first, what is the best approximation ratio you can get for this particular combinatorial optimization problem? And they said the ratio is such and such. Then he came with a quantum algorithm that beat it. And then they read his paper, and Scott Aronson blogged about it. And they said, oh, OK, well, we hadn't really thought that hard about the problem. And then they found a way to match the performance, actually to beat the quantum algorithm. Then the quantum algorithm improved, and I think now they're tied. So yeah, there could be a fast classical algorithm for factoring. Maybe someone knows it already. You never know. What can a qubit do? I guess I think I already took a sort of stab at it with the amplitudes. I guess I'll just say that it's not so much one qubit that's interesting, but n qubits. I don't know if Peter or Kristan want to say more.
So yes. So I think what is distinguishable for a qubit is its ability to interfere. And a qubit by itself is boring. Having n qubits gets really interesting because then you can start interfering more things. So that's why it comes. So exactly. So coming back to what Aram said, it's essentially the ability to have positive and negative amplitudes that interfere, cancel each other, and amplify certain things. For two bits, that's not very interesting. For n bits, that gives you 2 to the n numbers. You want to amplify something, then it becomes actually very interesting indeed.
Quadratic optimization.
So I think this maybe refers to the D-wave problem, or the problem that the D-wave machine solved, which is an NP-complete problem. It's just minimizing a quadratic function of n bits, which is NP-complete. And the answer is that we have heuristic algorithms for this. So we have two things. So first, we have a provable square root speedup over many classical algorithms, not just brute force search, but if you want to do like a tree search on a classical computer, backtracking tree search, you can square root that. And other classical algorithms we can do quadratically faster. Plus, we have heuristics like the adiabatic algorithm that appear qualitatively different than classical analogs like simulated annealing. So we would expect the instances on which they do well to be different, not necessarily a super or subset, than the ones on which classical do well. We don't think that they get an exponential speedup in every case, but they may get it in some cases. And I think, in part, this awaits smarter theorists. But I think it really, like with classical computers, it awaits empirical testing.
Yeah. So I'll take the last one. When will quantum computing be able to break current cybersecurity encryption? So what we need for breaking RSA and some other things is a few thousand logical qubits. So since we already have maybe 20 or 50 qubits, it doesn't seem like a few thousand logical qubits will be that far away. But these qubits are noisy, and to get a few thousand logical qubits, you need a few 100,000 physical qubits. And for these factoring algorithms, you need them to be really fast because you want them to factor in less than 30 years. So, first, if you believe in a quantum version of Moore's law, it's still probably a couple decades away. And we don't really know whether the quantum version of Moore's law is actually working yet, because we just have a few points on the curve, and you draw a line through them. It looks like it might be, but who knows?
Right. It could be that with a modular architecture, though, once you build a 20-qubit computer that has 3 links to other computers, it gets to the point where someone could throw a lot of money at the problem and quickly jump up. But we have a question from Charlie Bennett in 9 seconds. And the answer is yes. You can use Grover search because Grover takes a lot of iterations. And in the inner loop, you don't need to store the whole data set. It can just stream through the quantum computer. And I'm writing a paper about this now.
Too late.
I take that back. Negative time. OK. Thanks, everyone.